When power flows through a conductor, a magnetic field is created. If another conductor is located close to the energized conductor, the magnetic field induces a voltage in the second conductor. This induced voltage can be significant enough to energize sections of a building, even after the main power source is disconnected. This phenomenon is important to understand to ensure safety. Inductive coupling also plays a role. If a neutral conductor is open, the current flowing through the hot conductors generates a magnetic field. This magnetic field can induce a voltage in nearby conductors, including the neutral conductor itself. Consequently, parts of the building might remain energized due to the induced voltage in the neutral conductor. Capacitive coupling is another factor. Capacitance exists between all conductors, including electrical circuits and the surrounding environment. When a neutral conductor is open, the hot conductors become more positive relative to the surroundings. This creates a capacitive coupling between the hot conductors and the neutral conductor or other conductive surfaces. The resulting capacitive voltage can energize sections of the building. Furthermore, an open neutral can create a transformer action between the energized phase conductors and the neutral conductor. The hot conductors act as the primary windings while the neutral conductor acts as the secondary winding. This transformer action can induce a voltage in the neutral conductor, even if the primary power source is disconnected. As an example, if the neutral wire on the secondary side of a transformer opens, the voltage on the neutral conductor will rise to half the line-to-line voltage. This induced voltage can flow through the grounding system or other conductive paths, energizing parts of the building. To fully grasp the impact of these electrical phenomena related to open neutrals, it is vital to understand the principles of induced voltage, inductive coupling, capacitive coupling, and transformer action. Firstly, induced voltage is the generation of electrical potential in a conductor due to a changing magnetic field. When alternating current, AC, flows through a conductor, it creates a magnetic field that expands and collapses with the alternating current. If another conductor is placed within this changing magnetic field, a voltage is induced in that conductor. The magnitude of the induced voltage depends on several factors, including the strength of the magnetic field, the distance between the conductors, and the orientation of the conductors. Secondly, inductive coupling occurs when two or more conductors are close enough that the magnetic field from one conductor induces a voltage in the other conductor. This is similar to induced voltage, but inductive coupling specifically refers to the interaction between multiple conductors. The degree of inductive coupling depends on the mutual inductance between the conductors, which is influenced by their geometry and proximity. In the context of open neutrals, inductive coupling can lead to the energization of nearby conductors, even when the main power is disconnected. Thirdly, capacitive coupling arises from the capacitance between conductors. Capacitance is the ability of a system to store electrical energy in the form of an electric field. All conductors exhibit capacitance to some extent, both to each other and to the surrounding environment. When a voltage difference exists between two conductors, an electric field is established and charge accumulates on the surfaces of the conductors. This creates a capacitive coupling between the conductors. In the case of open neutrals, the hot conductors can become capacitively coupled to the neutral conductor and other conductive surfaces, leading to the energization of these surfaces. Fourthly, transformer action can occur when an open neutral creates a situation where the energized phase conductors act as the primary winding of a transformer, and the neutral conductor acts as the secondary winding. A transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction. It consists of two or more coils of wire wound around a common core. When alternating current flows through one coil, called the primary winding, it creates a magnetic field that induces a voltage in the other coil, called the secondary winding. The voltage ratio between the primary and secondary windings depends on the turns ratio of the coils. In the case of an open neutral, the energized phase conductors can act as the primary winding, and the neutral conductor can act as the secondary winding. This can result in a voltage being induced in the neutral conductor, even if the primary power source is disconnected. To further elaborate, consider a scenario where the neutral wire on the secondary side of a transformer opens. In a typical three-phase, four-wire system, the neutral conductor provides a return path for imbalanced currents. When the neutral is open, this return path is disrupted, and the voltage on the neutral conductor can rise significantly. The voltage on the neutral conductor can rise to half the line-to-line voltage or even higher depending on the load imbalance and the impedance of the grounding system. This elevated voltage on the neutral conductor can then propagate through the grounding system and other conductive paths, energizing parts of the building. This can create dangerous conditions for anyone who comes into contact with these energized surfaces. Furthermore, understanding the role of grounding and bonding is crucial in mitigating the risks associated with open neutrals. Grounding refers to the connection of electrical equipment and systems to the earth, providing a low impedance path for fault currents to flow back to the source. Bonding refers to the connection of various conductive parts of a building, such as metal pipes, enclosures, and structural steel, to create a common electrical potential. A properly designed and installed grounding and bonding system can help to minimize the voltage rise on the neutral conductor and reduce the risk of electric shock. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding in electrical systems. These requirements are designed to ensure the safety of people and property from electrical hazards. It is important to follow these requirements carefully when installing and maintaining electrical systems. The NEC Article 250 covers the requirements for grounding and bonding. Section 250.4 A5 addresses grounding and bonding requirements for alternating current systems. It requires that the grounding electrode conductor be connected to the grounded conductor at the service equipment and at the source of a separately derived system. The NEC Section 250.24 C discusses the grounding electrode conductor connection to the grounded conductor. This connection is essential for providing a low impedance path for fault currents to flow back to the source. The NEC Section 250.50 covers the requirements for grounding electrode systems. It requires that all grounding electrodes that are present at the building or structure be bonded together to form a grounding electrode system. This helps to ensure that all parts of the building are at the same electrical potential. The NEC Section 250.104 covers the requirements for bonding of metal water piping systems, metal gas piping systems, and other metal piping systems. It requires that these piping systems be bonded to the grounding electrode system to minimize the risk of electric shock. The NEC Section 250.118 lists the types of equipment grounding conductors that are permitted. These include wire-type equipment grounding conductors, cable armor, and metal raceways. The equipment grounding conductor is used to connect the non-current carrying metal parts of electrical equipment to the grounding system. The NEC Section 250.130 covers the requirements for equipment grounding conductor connections. It requires that the equipment grounding conductor be connected to the equipment grounding terminal of the equipment and to the grounding system at the source. When dealing with open neutrals, it is essential to take precautions to protect yourself from electrical hazards. Always assume that any conductor or surface may be energized even if the main power is disconnected. Use appropriate personal protective equipment, or PPE, such as rubber gloves and insulated tools. Follow lockout/tagout procedures to ensure that the power is de-energized and cannot be accidentally turned back on. Use a voltmeter to verify that conductors are de-energized before working on them. If you are not qualified to work on electrical systems, call a qualified electrician. Furthermore, be aware of the potential for backfeed. Backfeed is a situation where power from an alternate source flows back into the electrical system, even when the main power is disconnected. This can occur if there is a generator or other source of power connected to the building. Always take precautions to prevent backfeed when working on electrical systems. In addition to the specific requirements in the NEC, there are also general safety practices that should be followed when working on electrical systems. These include always working with a partner, keeping a clear work area, and avoiding distractions. It is also important to be aware of the potential for arc flash. Arc flash is a dangerous electrical explosion that can occur when there is a short circuit in the air. Arc flash can cause severe burns, blindness, and even death. Always wear appropriate arc-rated PPE when working on electrical systems that may be subject to arc flash. It is also important to be aware of the potential for step potential and touch potential. Step potential is the voltage difference between 2 points on the ground that are a step's distance apart. Touch potential is the voltage difference between a grounded object and a person's hand. These voltage differences can occur during a ground fault and can cause electric shock. Stay away from grounded objects during a ground fault and take precautions to avoid stepping on areas where there may be a step potential. Open neutrals can create complex and dangerous electrical conditions in buildings. Understanding the principles of induced voltage, inductive coupling, capacitive coupling, and transformer action is essential for ensuring safety. By following the requirements of the National Electrical Code and using appropriate safety practices, you can minimize the risks associated with open neutrals and protect yourself from electrical hazards. Additionally, regular inspections and maintenance of electrical systems can help to prevent open neutrals from occurring in the first place. Check connections regularly, especially in older buildings, and look for signs of corrosion or damage. Replace any damaged or worn wiring immediately. Consider using surge protection devices to protect sensitive electronic equipment from voltage spikes that can occur during an open neutral condition. Ensure that all electrical work is performed by qualified electricians who are familiar with the NEC requirements and safety practices. Educate building occupants about the dangers of open neutrals and what to do if they suspect a problem. By taking these steps, you can create a safer electrical environment for everyone. In summary, recognizing the potential hazards associated with energized buildings after power is cut, particularly due to open neutrals, is critical for safety. The convergence of induced voltage, inductive and capacitive coupling, and transformer action can lead to unexpected and dangerous electrical conditions. Understanding these phenomena, adhering to the NEC guidelines, and employing proper safety practices are paramount for preventing accidents and ensuring the well-being of individuals working with or around electrical systems. Remember to always prioritize safety and seek professional assistance when dealing with electrical issues to mitigate risks and maintain a secure environment.